Okay, like I mentioned last week and this Monday, I'll go over more practical problems. So I'll probably not to talk much in detail for understanding, but I'll probably tell you this is the way you can solve the problem or like approach you will do today. Okay, and also the Friday. You can also please make sure you watch the review on Friday. I did another one this morning. Obviously, I only could do first half of the review. So the other half will be on Friday. Please make sure you watch them on YouTube. All right, so the first one, I actually looked through chapter 1 and 2. I don't know how it's taught previously before I came into the semester. So I just tried to pick the ones that I think is quite important, and I kind of assume you guys know this anyway for almost 100% certain. But here's one potential problem you can might be see. So this is the one, okay? Maybe I'll do this one, okay? Here's the thing. So if we have 4 compounds, I tried it in the skeleton structure, so I didn't show you the hydrogen, but they're all there, okay? So first thing what you can do with this one, I probably think is maybe I'll give you one problem like this. I want you to find some hybrid orbitals. Okay. And this is kind of review like you see in the chapter 1. Can you guys find the sp2 hybrid orbital among those compounds? There might be the one potential problem you may see on the exam. So I'm not going to talk about how you can make the hybrid orbital. That'll take too much time. We have a lot of problems to go. The bottom line, the key element you need to look for this one is double bond. So whenever you look for sp2, you look for the one with double bond. So answer is B, right there. Once again, I'm sorry I don't have enough time to explain why. But this is the one way you can do. If I ask you to find the sp hybrid orbital, can you guys which one will be the answer? The one with triple bond, perfect, triple bond. So try to find the triple bond. Then obviously sp3, the single bond. So there are some single bonds there. So you can find which compound has the sp2 or sp1 hybrid orbital in the compounds. So maybe this is A, B, C, D, right? You could possibly answer for this one as like, this B is the answer. You're looking for sp1, C is the answer. If you're looking for sp3, A and D, right? A and D. So multiple numbers of the correct answer are there for this one. It makes sense, right? Do you want me to go in detail, right? I mean, we still have we want to save some time here, but this is the sort of a potential problem you may see. Basically, how many bonds you have. So there's another problem, another example I can give you from same compounds here. Maybe I can ask you to count the numbers of hydrogen hidden in this compound, a skeleton structure. So basically, all you need to remember from this type of question is that try to remember there has to be 4 single bonds on carbon. Either you can have a double and triple bonds. Whenever you have a double bond on carbon or triple bond, count the double bond as 2 and count the triple bond as 3, and make sure you need to have 4 in total on that carbon. That's all you need to know. So whenever you look at the skeleton structure, the first thing you can do is try to locate the carbon on each point of your compounds, right? That's pretty much it. And all you need to do is try to put the 4. Okay, so it'll be 1, 2, 3, 4. So it'll be 3 hydrogen here. 1, 2, 3, 4. There'll be 2. 1, 2, 3, and 4. Okay. 1, 2, 3, and 4. Okay, that's it. So you know the number here. And maybe you have, this one is 3, right? 3. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so you know there. It's the same. I'm gonna save some time. Oh, 1, 2, 3, 4. So no hydrogen. 1, 2, 3, 4. No hydrogen. 1, 2, 3, 3. There you go. And same here. 1, 2 on each carbon. 1, 2, 1, 2, 1, 2, 1, 2. So each carbon has 2 hydrogen. Right? That's it. Okay. So you can count this. This might be one of your possible potential problem. And now you're thinking, oh James, this I think I got a better way to do this. So say, oh sure, you can go ahead. What's this? Is this one? So you have arcane. You have a CnH2n plus 2, right? And arcene CnH2n, alkyne CnH2n minus 2. Okay, so if you just count the numbers of carbon, you automatically know if it has like, you know, this is the 1, 2, 3, 4. So hydrogen, you don't have to count it. That's just 10 right there. Because 2 times 4 plus 2 is 10. If it's the double bond, there'll be just 8. Because time just multiply by 2. And if there's triple bond, it'll be the 8 minus 2 will be 6. So this is how you can do this. So there's another possible problem you may see from here. That is this one. So if that is the truth, maybe I can ask you, oh, maybe could you guys find the some compound to show you CnH2n. Okay, and now you just tell me, oh, I found it. It's right there. It says double bond is alkene. So that is the answer. I got it right. Yes, you got it right, but only halfway to what? Perfect. So remember, the cyclic compound also has CnH2n, even though there's no double bond. It's just because of you have arcane, like a linear shape, but you have to make a ring structure. You need to sacrifice what? 2 like this. So even though the cyclic compounds do not have the double bond, still they will have C and H2n. So that's a tricky one. Remember this. If I ask to find this one, there will be 2 answers, not just one, because of this guy right here. Okay. All makes sense so far? We good? That's great. That is kind of something you can do. If I kind of twist your problem a little bit, what might be this one? So if there is a C n which is a 6, can you guys guess will be 2n minus 6? Perfect. There you go. So this is somewhat. So even though I know you know how to do Cn2n plus 2, Cn2 minus 2, I told you to remember the 4 bondings on carbon, double 2, triple 3, because you never know. You may have a combination of these two, either cyclic with the 1 double bond. Then you may have to do even further from what you know already from your memorization. So this is something, I think this is really good practice, especially for the beginning of the organic chemistry. So those are potential problems. You may just try to practice a little bit more. But obviously, this is kind of a review from the Gen Chem 1 and 2. So you guys do really well anyway. But just this giving you some idea what kind of problem you'll see on the exam. Okay? Can I move on? You good? That's great. You guys doing so far so great. That's great. So the next one, probably if I give you some the arcane structure, so this is maybe butane. Okay. Right. So we have I'm gonna do it again so you know how to do this. Okay. So if you have this one over here, you know why this is not in the linear. Okay, right? It's not why it's linear, right? You know, they are in just sort of a zigzag format because of this are actually tetrahedral structure. Okay, so do you know what's the definition of organic compounds? What's the organic compounds? What is the most important element in the organic compounds? Carbon. Perfect. So as I mentioned, carbon is group 4. They'll have a tetrahedral structure because it's not going to be tetra like planar because you have a 3D space in the reality. So that means you're going to have so many of this structure. I mean, some exception quite a bit, but most of the time you see a lot of this structure in your organic compound. So I'm not gonna lie, but I want you to remember the bone angle. I'll probably repeat this one on Friday. So watch that again. Just stick this number into your brain for whole your life, okay? I'm sorry, I'm not for whole your life, but for this semester. So there might be some question like if there's any something like this, it would be 120, or carbon dioxide, it would be 180. But I'm not gonna lie, just remember this number. That's the answer for the question. So whenever you have a tetrahedral structure, I'll point out that carbon, and I'll ask you to find the bond angle. Then you just need to pick this number right here. Okay? But just memorize it. I'm just doing this because not just for the test, but this is so important. This is the bond angle you cannot miss whenever you talk about the organic compound, or mainly made of the carbon chain. Okay, so this is why I cannot miss this question, which you know obviously what the answer is. Okay, all right, remember that one. Okay, all right, let's move on to the next one. Oh, is it there? Okay. So here's the thing. Whenever you have this one, hydrofluoric acid here, this is interacting with water. Okay, interacting with water. So if they're going to interact with each other, they're going to have obviously. So maybe you can say this is the acid here. We have water base. Nothing. Water is really base. Yeah, relatively speaking. And this is the other part here is like a sort of a residual, more precisely hydrogen throwing anion over here. So whenever you see it, it's one simple rule. I just want you to remember for the exam is once it's acid and base, they are going to be opposite on the other side. So do you have a question? Oh, okay. So if this is acid now, it might become fluorine anion over here. If you have a water here, it becomes hydrogen cation over here. If it's acid here, this is going to be conjugate base. So it's the other one, right? Once it's acid and here, conjugate base. And you have a base over here, and you're going to find this conjugate acid. So on your exam, I'm going to show you another set of the chemical reaction for the acid-base neutralization. And you may see this equation and see which one is your conjugate acid or conjugate base. So if you can tell me why this is acid here, why is it base, why is it conjugate acid or conjugate base, that's all you need to know. Because think about it, if you have an acid compound over here, this is become acid. What's the definition of acid here? They donate proton. So once they donate the proton, they become fluorine anion. That means in here, when you go on the other side, which is possible because it's a weak acid here, this is going to regain the proton to be in original form. That's why it becomes base in the other side. So same thing for water and the hydrogen cation. Once you get the proton to be hydrogen cation, but now it can also donate by becoming its original form, which was water. So it actually kind of act like an acid. So we call this conjugate acid. Yeah. Go ahead.
Does the term acid and base versus conjugate acid base always refer to the left side of the equation?
Oh yes, perfect. That's an awesome question. So whenever you have equilibrium here, you're going to have this one is acid and base. The other is conjugate acid and base. So there's no like a real term that become acid and base because they'll be determined by what?
pK.
pK. So it doesn't really matter. But if you see those on the left of your chemical reactions, you can see acid and base. On the right is a conjugate base, acid and conjugate acid, conjugate base. But also we're gonna do with the consider pKa value for sure. That's a very good question. So make sure you guys do this. So once we talk about the pK, that was actually my next problem I'm gonna solve. That's very good. So think about it. See, you have a, I don't know if you remember this. Oh, you had a question on the back? No, are we good? Oh, no, okay. So if you think about this one over here, I hope you guys remember this. Hopefully, if you're watching on YouTube channel video, this one is a strong acid here. This is strong acid here, and always it's going to be relatively speaking, right? There's no absolute justice here, but we can say this is a weak, relatively weak acid here. So think about it. This is a strong acid, this is a weak acid because the strength of the interaction between these two parts of the compound. So if these two are strongly bound to each other, they have a strong interaction, like here, they're not going to release this proton part of the compounds in certain conditions. But if it's those two interactions very weak, they are going to release a lot of this one, right? Protons here. That makes this one become strong acid. So you can assume that the strong acidic compound, you can estimate always almost 100% dissociations of those two. Become hydrogen cation, become anion, and most likely aqueous conditions. But this one, not really. That's what we mentioned about. They can go forward, reverse. So maybe some back and forth kind of interaction there. So for this reason, do you guys remember this? Stronger makes weaker acid. If it's weaker, it's stronger acid. It's kind of the other way. So please remember this. So whenever you look at this one, it actually kind of makes sense why this become weak acid, and also why it has a stronger interaction if you look at the periodic table. But I don't have a time, I'll move on. So if you have whenever you have a not strong acid or strong base, maybe you can have a weaker or weak base or weak acid. We need to know how strong that the dissociation on the reactions, right? Because the main part is how much they can go over dissociate into the system. So then we have the number for Ka. This is why we're using Ka value. This will tell you how strong your acid compound will be in certain conditions. But obviously, if you have a strong acid and base, you don't need it because they're almost 100% dissociate anyway. So those are the only usually for the weak acid and weak base. So you can have Ka or Kb, like you learned in Chem 2 the last semester. Anyway, so if you have a Ka, there's very simple potential problem here. You can see, I'll give you the number for Ka. Okay, I'll give you the number for Ka, and I'll ask you to get the number for pKa. That's it. How easy the question can be, right? So you look at do you remember pH, right? You use the concentrated hydrogen cation. We do the same over here. This is the p value of Ka. That means the negative log of Ka. So you bring your calculator next week for the exam 1. Put the negative log on your calculator and plug your number that you're given on the exam. So maybe this is something like this one. Okay, you just plug this number into here. Okay, so plug that Ka value into negative log, and whatever the number it comes in your calculator screen, that's the pKa. That's very easy, right? So this is just one step easy calculation. We'll give you a number for pKa, so you can have some idea. So maybe you can think, oh, maybe I might twist a little bit in the other way. So maybe I'll give you a number for pKa, and I want you to get the Ka value in the other way. It's pretty much the same. So either negative log is of 10, right? So if you go backward, it's 10 powered by negative pKa. That will be your Ka. So either way, you're gonna put the Ka to pKa, or you can also try to get the number for pKa in the question. You can put it in the Ka value. So there will be, I think, quite easy calculation problem you may see on the exam. Okay. I'm not gonna spend more time on this. It's pretty much that's it. So, oh, can I move on? Okay. All right. So this is some of the part in I think it's chapter 2. Yeah. So let's move on. Okay. The next one. Oh, yeah. So another one I think is quite important too is to try to find out the formal charge of each atoms in the compound. So if you have compounds looks like this, okay. I know, once again, like I said a month ago, you can also try to use the equations. You have numbers of electrons in the bond divided by 2, or you can get the numbers of the lone pair times 2, plus add all the numbers to get the formal charge and everything. That's fine. But I think what I personally do is much easier. I personally believe it's easier, is this one. Okay? So if you look at this one, all you need to do is you just circle your target atom in the compounds. And if you look at just the bond here, right? This is the bond between two dots from hydrogen and carbon here. So if you circle this one over here, you have a 1 dot in the circle, okay? And you know hydrogen is group 1, okay? Group 1, and you have a 1 dot here, so it becomes neutral. So one group 1 has 1 dot there, or it's neutral. So carbon here, we circle this one over here too, so it'll be 1, 2, 3, and 4, okay? 1, 2, and 3, 4. But carbon is group 4 elements. You have a 1, 2, 3, 4 dots there. Oh, so it becomes neutral here too. There, no problem. But if you look at this one, center sulfur here, you have 1, 2, 3, 4, 5. So as a lone pair, you count this as a pair of electrons, so it would be 1 and 2. So it would be 1, 2, 3, 4, 5. But the sulfur is group 6. So it means it's missing 1 electron. But as you know, electron is negatively charged particle. We wonder if it's really a particle or not still even nowadays, but anyway. So the 5 electrons, but they're group 6, it should have a 6, but only 5, so missing negative, meaning it's positive, plus 1. Because it's missing negative charge, meaning it's gaining a 1 positive charge, it's the same deal. So this center sulfur will have a 1 formal charge here. Okay? 1 formal charge here, 1 plus formal charge. Here we have 3 lone pairs, so it'll be 1, 2, 3, 4, 5, 6. And another one from this single bond, so it'll be 7. Okay? So it'll be 7 dots in here, but the oxygen is group 6. Group 6. So it has more than 1. So it has additional electron, which is also what? Negatively charged. This is why it becomes negative one negative charge here. Overall, this compound has 0. Okay? So it's just because of these two. So obviously you can see it's become quite unstable, carrying 2 additional opposite charges on the center. Okay? But whenever I ask you to find the formal charge on oxygen or sulfur or carbon and hydrogen, you need to say, oh, this is -1, +2, 0, and 0, and so forth. Okay? That's pretty much it. So I think this is easier this way because the only thing you have to do is circle around that specific elements on the compounds and just count the dots and see where is it in the periodic table. So periodic table will be given. You will see where there's the elements in the H groups and everything. I think it's also pretty much Jenkins 2, so I'll move on. But this will be one potential problem you may see on the exam. Okay. All right, let's do a bit more. And I think that'll be all for today. I'll do the other half in the The next one, okay. So, whenever you have the phosphate, okay, what you can do is you're always going to draw the first element you see in the chemical formula as a central atom. So that is phosphorus here in this phosphate anion. So I'm gonna put the phosphorus at the center, and gonna put those 4 oxygen as the surrounding atoms around. Okay. And whenever you see this one, what you can do is you can assign this the 4 charge, -3. Obviously, it's an anion, polyatomic anion. Usually, if you look at the periodic table, the oxygen is more electronegative than phosphorus. So I'm gonna assign the negative charge on those 3. Okay. Like this. So whenever you can actually memorize this one for good for organic chemistry. 99% chance whenever you have a oxygen that carrying the negative charge, they're always a single bond. Always single bond. Always single bond. One single bond. Not 2 single but 1. Always. Like 99% chance. And when it has a double bond, it always neutral. So 1, 2, 3, 4. Only one exception is when it's attack the other atoms, and with this lone pair that makes positive, but most of the time in the stable condition they just become neutral. So this is the one you can draw, but as a resonance structure wise, you're going to have other possible resonance structure of this one by moving there's a lone pair on the lone pair and the double bonds to other side of lone pair, and double bond. So those are here. Okay, so maybe you can put it on the top or to the side. Okay. So in your exam, I'll give you one structure that is not one of its possible resonance structure, and you need to pick it up. So those are all 4 possible resonance structure, but there'll be one like okay. So this is also possible. No, not really, because of the. Do you see this? Why it's not very possible? I don't have time, but yeah, I'll move on. But so those are the answers, but fine. Those ones are theoretically possible, in reality not really, because of the charge and double bond. Or I can give you one thing like this. It's even worse. Can you guys see this? What's the definition of double bond? What's the double bond is made of? Sigma bond and what? Pi bond. And you got the pi bonds in the 90 degree. Good luck with that. Okay, anyway, so let's move on. But does it make sense? We good? Okay, to try to get the resonance structure, just moving the double bond or the lone pair around to make the either this one has double bond, this one. In reality, just for your understanding, it's not on the exam. Just for your reality, what they see is this one. Maybe if you took my Gen Chem 2, you maybe remember this one. This is not on the exam, don't worry about it, just for your understanding. This is the reality, because we see in modern chemistry, we only see this as a electron cloud. The cloud means like it's like some density thing. So that means we actually using chance, using mathematically constructed optimum value to find the chance to find the electron in the certain area. So it's more like a cloud thing. So it kind of show you a hybrid resonance structure. That's what we normally see in the experiment, actually, in reality. So those are possible for sure, but just for our understanding as a resonance structure. Anyway, I'll move on. You don't have to know this one, but those you can try to practice a little more with other possible resonance structure. But there will be one obvious structure you say, oh, can't be this. You will pick that one. Okay. All right. So far so good. Let me go over a few more things. Okay, so here's the thing. One of the important part of chapter 2, anyway, chapter 2 is intermolecular force. Okay? Intermolecular force. So I'm not gonna lie, I said this also this morning. Whenever you see this type of question, where what might be the best intermolecular force here, or sort of kind of question, you don't even have to think. The answer is hydrogen bond. Yes, I'm telling you the answer right now. So just pick those hydrogen bond. I'm also doing this for go ahead. I'm sorry.
I'm sorry.
Yeah.
Can you say, can you repeat it?
Yeah. So whenever you see this type of intermolecular force related question, answer is just hydrogen bond. I'm just telling you this. It's the same for the bone angle thing. So the reason why I'm doing this for you guys is the hydrogen bond is so important in the organic chemistry. If you think about the dipole-dipole interactions, which always comes from the polar compound, right? Then those dipole moments or everything, among those all types of dipole-dipole interaction, this is the strongest one because when it has the all covalent bond to the electronegative elements in the periodic table, as it says in the intermolecular force, there are going to be other parts of either oxygen or fluorine and nitrogen will be strongly interacting with those hydrogen and other compounds, or the same, probably same. Okay, so this is so strong because if you look at the size of nitrogen, oxygen, fluorine, they're pretty much small, and also they're quite love pulling electron to themselves. So they are going to have quite a very strong force between those two. So we named this specially hydrogen bond, which is simply just also one of the dipole-dipole interactions, but they become so important for us, the scientists, we named it specially as hydrogen bond. So this is something you cannot miss. So maybe I know you guys haven't gone to much of the functional groups yet, but you probably know this one anyway. It's very common. It's methanol, right? It's a one carbon meth, but it's the alcohol is methanol. So if you look at this methanol here, okay, those two, I'll draw more specific. This can interact with the other hydrogen. They also covalent bond to oxygen as well here. So the hydrogen bond is the strongest intermolecular force that the methanol can experience. They can also interact with other part, which is pretty much non-polar. So the other part of the methanol may experience much weaker interactions than hydrogen bond. But that is for possible in one side in certain special, interaction in a certain angle and a certain proximity, they will have very strong interaction. We call this hydrogen bond. So make sure you guys remember hydrogen bond sometimes play a very, very important role in a lot of chemical reactions and the biological mechanisms. Guys taking bio too? Do you remember the DNA complementary? Very good. This is why we have a GC contents and everything for PCR condition. But anyway, let's move on. See I think that's pretty much it. It's only been 35 minutes. Okay. Yeah, I'm sorry. That's already done. I did this one. It took me a bit over 40 minutes. So I finished there. But this is what I did this morning. So to be fair, I'll finish it here. I'm sorry. We have some time. But I'll do the other half of the review on Friday. So make sure you guys watch the YouTube video. It's interesting. It took me only 35 minutes today.